This segment, we're going to talk about isentropic relationships for ideal gases, and we're going to start with those equations for entropy change that we derived from those TDS equations. So these are equations for entropy change for an ideal gas. This one's just if you don't make any assumptions about specific heats being constant, and then of course we've got two equations where we do make that assumption. We're going to manipulate these to get some nice convenient relationships for isentropic process, for ideal gases undergoing isentropic processes. And we're going to consider two cases, one where we don't make the assumption that specific heats are constant and one where we do. So let's take the one where we don't make the assumption that specific heats are constant. So here's the equation for entropy change for an ideal gas. And for an isentropic process, which are what these equations are going to be valid for, delta S is equal to 0. So I just set the whole thing equal to 0. And I rearrange it to get P2 over P1 by itself. So I've just brought some stuff on the other side of the equal sign, raise everything to the exponent to get rid of that natural log. I distribute the specific gas constant, and then I just rearrange it just a little bit to get it in a nice convenient form, because I'm going to define a new property, which is the relative pressure. And this relative pressure, which is equal to E to the S naught over R, where R is the specific gas constant, this is a dimensionless quantity, and it's tabulated in those ideal air tables. So this is where I've been telling you not to use that column. This is the time that you can use that column. You can see it's only a function of temperature. So if you know the temperature, and of course if you know the internal energy and enthalpy, you just read it right off the table. All right, so there's our first isentropic process valid for an ideal gas undergoing an isentropic process. And now we're going to manipulate this equation and then use the ideal gas law to get an equation in terms of the specific volume ratio. So here's my ideal gas law, and I know that if this thing behaves as an ideal gas between state 1 and state 2, then these quantities are equal to one another because they're just equal to 1 for an ideal gas. Then I'm going to rearrange it to get it in terms of P2 over P1, because I know for an isentropic process that P2 over P1 is equal to the ratio of relative pressures. Then I can rearrange this to get it in terms of the specific volume ratio. And you'll notice that the R, the specific gas constant, dropped out. And now all I've got is T2 over PR2, which is... I'm going to define a new thermodynamic property, which is the relative specific volume, which is T over PR. And that T, remember, is an absolute temperature units. It's a dimensionless property, and it's the other thing that's tabulated in the ideal air tables that I've been telling you not to use, but you can use it now. So it's not specific volume, it's relative specific volume. No units there. All right, it's only dependent on temperature. So if you know the temperature or the enthalpy or the internal energy, you can look it up off the table. All right, so let's see what else we've got. So those are our two isentropic relationships for an ideal gas, only valid for ideal gas undergoing an isentropic process. Now let's consider the case where we do have constant specific heats. So I've got two equations that I can use to calculate changes in entropy. I'm just going to pick the one where one with CV. It honestly doesn't matter. I could have picked the one with CP, but I just had to pick one first, so I'm picking this one. For an isentropic process, this guy is equal to 0, so I just manipulate it. And I'm going to bring one of these terms on one side because I want to get an equation for T2 over T1. So what I'm trying to do here is I need to get the natural logs with nothing in front of them so that I can raise everything to the E and get rid of those natural logs. And so what I'm going to do is I'm going to, instead of having the negative R over RC in front of that natural log, what I'm going to do is I'm just going to bring it up there as an exponent. And then I'm going to get rid of the negative. And the way I'm going to do that is I'm just going to flip that V2 over V1 so it becomes V1 over V2. And now I've got the natural logs with nothing in front of them, so I can raise everything to the E and get rid of that. All right, so that R, for an ideal gas, the specific gas constant is equal to Cp minus Cv. That's just by definition. So if I distribute that, well, I see that in my exponent, the Cv over Cv, that's just going to become 1. And that Cp over Cv, by definition, this is that K value. So for air at 300 Kelvin, it's 1.4. All right, well, there's my first isentropic relationship for an ideal gas undergoing an isentropic process with constant specific heats assumed. Whew, that's a lot of stuff. And then what I could also do, since I used that CV equation to get this first isentropic relationship, I could use the CP equation as well. I could do another similar manipulation and I would get things in terms of the pressure ratio. And then I could combine both of those together and I could get things in that relate the pressure and the specific volume ratio as well. So those are it. I've got 5 equations so far. I've got 2 that I can use if I do not make the assumption that specific heats are constant, and I've got 3 if I do make the assumption that specific heats are constant. So the nice thing about assuming that specific heats are constant is I can directly calculate things like temperature and pressure and specific volume for an ideal gas at the end of an isentropic process. I can calculate that directly. As opposed to if I don't make the assumption that specific heats are constant, then I'm left having to look into my ideal air tables at those PR and VR values, and I'll probably have to end up interpolating for some things as well. So, all right, well, I hope that was helpful. We'll work some problems the next time we meet, and I will see you then. Thank you for watching.